Hello everyone. Welcome back to Digi Structures, and today we'll be using the slope deflection equation to solve a statically externally indeterminate structure. So let's get into it. So right here we have a structure, a beam. Let's give it a, let's call this B, let's call this C. Now, of course, it's an indeterminate structure. We have three reactions here. We have one reaction, we have three reactions, making 7 reactions, and we just have 3 equilibrium equations. So we need 4 more equations to solve this, but that's not even the point. The point is that it is statically indeterminate. So we have to resort to any of the methods, whether first methods, whether what's the name? Displacement method. But in this displacement method, we're using slope deflection in this video. So let's get straight to it. Now the first step in using the slope deflection equation is to, remember the expression is m equals to 2ei over L, open bracket, depending on the near end and the far end, 2 theta plus theta, once again depending on the near end and the far end, then minus 3 times the chord rotation, close the bracket, plus fixed end moment. So let us compute for the fixed end moment first. So remember that in the fixed end moments, we assume that all the supports are fixed. Of course, we'll be assuming that it's fixed. So FEMs, fixed end moment. So I have this. You always draw your diagrams. 10, 18 kilonewtons. So now I'm assuming that, because in my derivation for m equals to 2e over L 2 theta, I assume that, okay, anticlockwise is positive. And remember that derivation that I did earlier in the, you can check it out, slope deflection derivation, you see it there. So I use this sign convention where counterclockwise was positive and clockwise was negative. So once again, in the convention for fixed end moment is this way, where if this is A and this is B, I have FEM AB and I have FEM BA. So FEM AB, because of the counterclockwise nature, would obviously be positive. So positive times, now going to our fixed moment tables, we'll be having PA B square over L square Well, where did that come from? A minute. Didn't erase properly. Wow. Well, so we're just going to have to copy it. I'm sorry. And move it straight to copying it. Just a minute. Just a minute, neglect all of this. So, Ctrl V. Yes, I'm sorry. So, too much of structural analysis. Yeah. So FEM, as I was saying, FEM AB, based on the expression, if we get to Aslam Kasimali or at the back of the book cover, you will see the fixed end moment expression. You can just search for it on Google. So PAB square L. So where this is A, always A, this is B. So this will be positive 18 times 10 times 15 square over 25 square, where this gives me plus 64.8 kilonewton meter. Now, FEMBA will be negative because of the clockwise nature, negative PA square B over L square. That will give me 18 times 10 square times 15 over L square. L square is 25 square. 25 square equals to minus 43.2 kilonewton meter. So now that we have our fixed end moment for AB, we'll do the same thing for fixed end moment for BC. So once again, I have this. So I have 2 kilonewton per meter. I have 30. I have FEMBC. I have FEMCB. So from the fixed end moment expression, once again, due to the anti-clockwise nature of AB, I'll be having plus WL square over 12, which will give me 2, where W is my load intensity, times 30 square over 12, which will give me positive 150 kilonewton meter. Yes, that's our guy. And now the FCB give me minus WL square over 12, which will give me the same thing. I mean, same in magnitude, but different direction. Check it out. So next thing after computing your fixed moments is to write down your slope deflection equations. Write it down. So writing down the slope deflection equations. Writing for each of the member ends. That is writing down or just basically saying give me the expression for moments for each of the member ends exactly. So I won't have to write it. You can, so it won't take time, it won't take hard time. You just have to get to the point. So once again, the next step is to write down the expression for the moment for each of the ends of the members. So for this structure, once again, we'll be having the structure when we decompose it. We'll be having a member moment here, and I'm sorry, we'll be having another member end moment there. We'll be having a member end moment here. We'll be having another member end moment here. So let's get to it. So The first one will be when we decompose it, or in fact, let us copy the structure again for our convenience. A minute. Select and select it, copy it, and paste it. Recently, I made a mistake when doing something physically, and what came to my mind was Control Z. Control Z came to my mind. That is, let me undo what I did. I mean, a physical action, or for that matter. So let's get straight to business. I may be pasting it. So I have this once again. So decomposing my structure, I'll be having, let me use the blue, static. Okay. And yeah, remember that when I derived this expression, I assumed that the member end moments were counterclockwise. So counterclockwise. Exactly. Where this is 10, 15, 30, of course a UDL. A UDL to 30 kilonewton per meter, 15 meters, 10 meters. So where this is A, this is B, this is B, this is C. So it means that my moment will be MBC, MCB, MAB, MBA, where A represents the near end for this particular beam. Where A for this particular moment, for that particular member, AB represents the near moment, the near end. So, at that joint, we call it MAB, where B will be the far end at that particular location, that particular section or member of the beam. While for MBA, where B becomes the near end and A becomes the far end. Similarly, for BC, where B becomes the near end and C becomes the far end, like that, in a similar understanding. So I believe this is 18. Yes, 18. So writing down the expression, MAB will be equals to 2EI over L, open bracket, 2 theta A plus theta B minus 3 chord rotation plus FEM AB. So writing it down, MAB will be equals to 2EI over L is 25 2 theta A. Remember that theta A will be 0 because we had a fixed end there. I remember for the boundary conditions, remember when we did boundary conditions, for a fixed end, the slope is 0, the rotation is 0. So we have theta B. Similarly, there's no chord rotation, there's no settlement, so there won't be any chord rotation. So we just have this expression plus FEMAB. FEMAB is 64.8. Yes, I believe so. Yes, 64.8. Now, this is equation 1. Similarly, MBE 2ei over 25, open bracket. Now this time it will be 2 theta b plus theta a. Now once again that guy is 0 chord rotation plus FEM AB. FEM AB is FEM BA rather is minus 43.2. So MBA is 2ei over 25. Now A is 0, theta A is 0. Once again I explained it. So 2 theta B minus 43.2. So this is equation 2. Now MBC 2ei over 30, 2ei over L, 2 theta B plus theta C minus, of course, that guy is 0, no settlement, no sinking, plus FEMBC. FEMBC is 150 kilonewton meters. So once again, theta C is 0, fixed end boundary condition. So MBC gives me 2ei over 30 to theta B plus 150. Equation 3. Now similarly, MCB gives me 2ei over 30, 2 theta C plus theta B, sinking is 0 plus minus 150. I mean, this time is now a clockwise moment, if you remember. Now this guy is 0, so we say MCB. Let me just erase this. So we say MCB is equals to 2ei over 30 theta B minus 150. Now is equation 4. The next step is to apply equilibrium equation, just one, which summation M is equal to 0 for the joints. For joints that are free to rotate naturally. So, looking at this structure once again, A can't rotate, C can't rotate, B, based on the boundary condition, can rotate. So we say that we're applying equilibrium equation of summation MB is equal to 0. Summation MB is equal to 0. So once again, if my joint B is here, and based on Newton's law, Newton's third law, just basically saying that action and reaction must be opposite. So it means that I must have a moment here. Since this is moving anti-clockwise, I must have one moving in this manner, clockwise. If this is moving anti-clockwise also, I must have one in this manner moving clockwise also. So clockwise, this is B. So in traveling to this point, and applying moment at B equals to 0, then these two moments, I'm looking at the red ink now. This moment in red ink, that is the arrows, I can see that. The way I like to think of all these summations of moment, all these things, that for moment, I like to think of it as summation of anti-clockwise moments is equals to summation of clockwise moments. So if I do that, I can just say that, okay, or let me just continue. Let me name it first. If this is MBA, if this is MBA, or let me use blue ink. If this is MBA, it means that this guy too would be MBA. Similarly, this guy too, this guy would be MBC. This guy. So it means that applying equilibrium equation, I'll just say MBA plus MBC is equal to 0. Simple. So taking it downwards now to where I have my other guys, MBA plus MBC is equal to 0. Please, in your notes, I'm sorry for just writing my notes this way, but I'm sure that in your notes, you should make it much more orderly. And I believe that we are taking notes down. Taking notes is an efficient tool for writing, for learning rather. So MBA plus MBC, MBA plus MBC equals 0. Now substituting my slope deflection equations, remember MBA was 2EI over 25. MBA was 2EI over 25 times 2 theta B minus 3 this thing, but it cancelled, minus 43.2. This was MBA. Now MBC, 2EI over 30 2 theta B. Theta C was 0, so plus 150 equals 0. So, knowing this, I can say that 0.08 EI to theta B minus 43.2 plus 0.066 EI to theta B plus 150 equals 0. So I can say that 0.16 EI theta B plus 0.132 EI theta B plus 106.2, 0.8, sorry, when you calculate it, when you sum these two, you get this, it's just basic maths. So I can say that EI theta B is equal to minus 365.75 kilonewton meter square. Exactly. I have this in mind. So the purpose of this equation is to get the rotations, but of course in terms of EI. So you can then substitute, because the impediment to solving this MCB, this MBC, was that we didn't know theta. We didn't know theta B, because theta B was the common one in her, was the only one rather in her. So we didn't know theta B. So the only way we could get theta B was when we applied this summation of moments at that joint. And now that we've gotten theta B, now we can find all the moments by substituting this expression back into the moment equation. So doing that, coming back, substituting theta b, I have NAB will be equals to or let me start with okay, or let me just do MAB first. Will be equals to 0.08 theta BEI, so times 2 over 25 0.08 times theta BEI, which we just got to be minus 365.75 plus 64.8 MAB would now be equals to, when you get everything, you get 35.54 kilonewton meter. Of course, since this is positive, then it means that what we got here is a counterclockwise moment. Can you now see? Now MBA, let's go to MBA. Looking at this, 2 over 25 times 2, which will give us 0.16 theta BEI. Now theta BEI is minus 365.75 minus 43.2. So MBE would give me minus 101.72 when you calculate it, kilonewton meter, which is equivalent to just saying 101.72 is the same thing, kilonewton meter, but clockwise. So now that we know MBE, we can know BC directly, because we remember this equation in red before, this red guy, when we found the summation of moments. I'm using colors to associate some things, which is also a tool for learning. So MBA, remember when we did this red guy? So it means that MBC will also be 101.72, but in a opposite way, because if MBA is minus 101.72, then MBC will be equals to, when you carry this to the other side of the equal, then you have minus comes to minus, then you have positive kilonewton meter, but now anti-clockwise. So we don't need to solve for the slope deflection and stress ourselves when we have one sweet equation. So the next one now is MCB. Sorry. MCB is the next one. MCB. MCB equals to 2 over 30 times EI theta times minus 365.75 minus 150. Just the same thing with this equation, basically. Now what I'm just doing, you can check it out, see. I hope that I'm passing on an understanding. Please comment in the comment section if you find this video helpful, And please also help me like this video so that more students across the world can have access to wonderful content like this. So this semester I this semester that I'm in currently, funding level, first semester, it's quite a lot. So I would still try my best to make more videos, but I'll still do it. I'll still be making more videos, but it won't be easy. But I would really appreciate if anyone watching this video right now can, send this video to his friends that would need it, especially friends in this industry, civil engineering. Just send. You never know who you may be helping. You never know who may even need it. Thank you. So MCB is equals to minus 174.38 kilonewton meter. So we have our moments. So coming to this place, we have zooming in. Yes. So I'm moving here. So I have MAB, I have MBA, I have MBC. So rejoin my structure, my decomposed structure. Remember that this is my structure once again. Well, let me see if I can still paste it. Exactly. So decomposing the structure, once again, I'll be having this guy. I'll be having a straight guy. I'll be having this guy also. And in this joint. So my moments at AB is 35.54. 54. Okay, let me draw it much more better. So right, this is joint B. Right, this is the other guy. Now I'll be having a UDL. So 30. Now I'll be having a point load 10, 15. But now once again remember that this is A, this is A, this is B, this is B, and this is C. So it means that of course I'll be having my reactions member end shears, which I will use to get my reactions, especially for B. But now the most important thing is that now that we've gotten our moment, this is the next step where we just apply our moment. The moment we go here, this moment, it was a anti-clockwise one, so 35.54 kilonewton meter. I'll be having MBA moments which I got from this guy MBA, which is 101.72, 101.72. MBC, which is 101.72 also, 101.72. In fact, the moment at that area will just be 101.72, so you can just put a single 101.72. So MCB would be minus 174.38, which is equivalent to clockwise moment, 174.38. So it's kilonewton per meter. So this is the guy that we're dealing with. So let's just have a boundary line. So we'll be applying the equilibrium equation to each of the members. So applying equilibrium equations to member AB first. Now, remember that I've gotten my member end moment. Then now I splitted my structure. Then applying the member end moment to my structure where it is supposed to be. Remember, it's always a member end moment. You get. But now the purpose of now applying these equilibrium equations to each of these decomposed members is so I can get AY, so that I can get BY1, so that I can get BY2, which will then generate RB, which is my reaction at B. Then I can generate CY. That is the purpose for applying equilibrium equations to each. So applying equilibrium equation to AB, starting with summation Fy equals to 0. So summation Fy is equals to 0. So AY plus BY1 will be equals to 18. So similar fashion, still member AB. Okay, let me just put it underneath. So similarly, summation MA for member AB is equal to 0. So still on member AB now, still on member AB. So summation MA is equal to 0. If summation MA is equal to 0, it means that I'll be having, think of this place as a ball where it can rotate. So 18 will move it clockwise. 101.72 will also move it clockwise. 101.72 will move the ball clockwise. 18 will move the ball clockwise. So I have 2 clockwise. 18 and 101.7. So 18 times 10. Because that's the moment. 18 times 10 plus 101.72 will be equals to anti-clockwise, which is 35.5 per moment, plus the 25 by plus 25 by, because of the length is 25. 25 by. Well, so here I can say by will be equals to 9.8. Solving it mathematically, then I can substitute it back here, and I'll obtain AY. So BY1 rather, and I'll obtain AY to be 8.153 kilonewtons. So doing the same thing for member BC. summation Fy is equal to 0. So I have By plus Cy is equals to 60, because 2 times 30 is 60. Then I have B is equals to 0. This is B, a ball. So what will rotate it clockwise? 174.38 and 2 will rotate it clockwise. So it will be in the same side. 174.38, which is a moment already. No need to convert it to this, no need to multiply it. Plus 2 times 30 times 15, all clockwise, will now be equals to anti-clockwise. 101.72 plus 30 Cy. You can take a look. Doesn't it make sense? This will be anti-clockwise, anti-clockwise. This also, moving on the ball, will be anti-clockwise. So Cy from this would be 32.42 kilonewton. By2 will be equals to, when you now substitute it here, it's supposed to be 2. You'll be having 27.58 kilonewtons. So moving back to my green ink. So looking, now that we have the member end shears, then it means that our reaction at A will be 8.153. Our reaction at C will be 32.42. Our reaction at B will be By1 plus By2. You can check it, By1 plus By2. So which will be 37.427 kilonewtons. So I can redraw my structure. Let me make it big. So this guy, now I'm making it bigger. I'll be having this in my structure. I'll be having this. I'll also be having this. Sorry, it's not inclined. It is not inclined. What? Oh, why is it hanging? Okay. So then my UDL, then my load, my load 18, the moment, load, another moment, can you see now we use our moments to now get our reactions. Then now we have what we need to get our shear force and bending moment, our stress resultant. 2 kilonewton per meter, 10, 15, 30. So, of course, shear force computation. Let's have the computation. Let's have the computation. So, of course, if this is A, if this is B, and this is C, then FE would be plus 8.153 kilonewton. BC, and if this is D, FD will be 8.153 minus 18, which will give me minus 9.847 kilonewton. FB will give me minus 9.847 plus this guy now takes it up plus 37 points plus 37.427 plus 27.58 kilonewton. FC prime 26.58 minus, okay, why is the FC prime? So if this is B, remember that UDL normally the shear force, the action for this is a varying stuff, so uniformly distributed loading, so it is not just a single point load. So because it is spanning across, then effect 2 on shear force and bending moment will also be across the beam. So it means that just before 2 kilonewtons from this guy as its effect, we'll be having the total effect from this UDL here before 32.42 would have its effect. So that's why we name it FC prime. So 2 times 30. So as for the UDL, the final effects of the UDL, FC minus 32.42 plus now 32. So 0, correct, 0 kilonewtons. Now our bending moment. And the computation. Now, I love to cut my beam for bending moment. So I will start my cut from here. XX. I'm doing my cut here because if I cut it here, I can find the bending moment at D and I can find it at B also. Do you get? Obviously, if I also cut it here, I can find the bending moment at D, but I won't be fast. Now, don't do this for shear force. For shear force, you do it gradually. I'm doing it. Now, because shear force is because the forces, let me just put it this way, that you understand, the forces are quite insignificant to bending moments. So when you, irrespective of whether you place this cut, whether here or here, you have the same bending moment. Do you get? So before we now proceed, we'll be using this one only. This one. So before we proceed, you should know that MA is minus 35.54 based on our bending moment convention. Remember that when it tries to pulls the beam, when it tries to bend the beam in a direction that bends it downwards, the bending moment is negative. But when it tries to bend it upward, it is positive. So that's our convention, remember. So minus 35.54 at A. Kilonewton meters. Now, this other one. Now cutting it like I said. 18, 10, x minus 10, x, 8.153. $55.54. So mx is equals to 8.153. Obviously from here to here is x. 8.153. So is the moment, so we're converting the force to a moment, so times perpendicular distance, which is x, minus, now this guy here, 35.54, is trying to pull it in a direction. It's trying to put our beam in a downward direction, and that convention will be minus. Now also 18 is trying to put our beam in a downward direction, and that convention is minus. That's why it's minus 18. X minus 10. So solving and solving, be having this, and x is equals to minus 9.847 x plus 144.46. Now placing mg is when it is at 10 meters. When you place it in this equation, when you place 10 meters in x, you'll be having 45.99 kilonewton meters. When you place for MB, what is the distance from B to M? For MB, we'll be having 25, x must be 25. So placing it, will be having minus 101.705 kilonewton meter. You know this, keeping it in mind. Now, which other points do I need to know the bending moment? I know bending moment for A, D, and B now. Now, I also know bending moment for C, which is minus 174. Minus 174 because it tries to pull the beam downwards. Minus 174.3. Now, I also need one more, which is for the UDL, the maximum bending moment for this UDL. But I can't move here. No, I don't want to waste time. I would prefer to move in this direction instead. Moving in this direction. So moving in this direction, I would have this. I'll be having this. Of course, I'll cut it here in the UDL. Of course, this is MX. Now, once again, doing this, you can either Okay, let me pause on this. 32.42 x, and there was a moment here. There's 174.38. So you can either say summation. Once again, I think I've mentioned it before, summation m for this thing is 0. Just like you can also do it for the one we just did, where for that one we didn't do summation m. You get the same answer instead of using convention and bending moment convention that will try to pull it downward, where you say that one is negative, where the one that tries to pull it upward is positive. You can just say summation m is equal to 0 and use your normal clockwise equals to anti-clockwise, and you get the same mx. But instead, I prefer to use the bending moment convention, where the one that is trying to pull the beam upwards is positive. So mx, I just put mx straight, is equals to 174 minus 174, bringing it downwards, plus 32.42x upward. Now this is 2 minus 2x squared over 2. So I'll be having mx is equals to 32.42x minus x squared minus 174.38. So, well, now the point of getting this equation is so that I can know the points where my bending moment is 0, is maximum rather, and to know when something is maximum, the position, of course, the mass, x is equals to 0. So doing this, we'll be having, differentiating the above expression, we'll be having 2.42 minus 2x is equals to 0. So x will be equals to 16.21 meters. Substituting x into this equation back for mx, because that is the purpose. We found the position where mx will be maximum. So that position now, let's substitute it back inside mx. You'll see that we'll be having m max, which is equals to 32.42 times 16.21 minus 16.21 square minus 174.38. We'll be having 88.38. So once again, let's draw our surface and bending moment diagram. Let me use this place to draw it. So this is my beam, this is my load, this is my load, this is my load, this is my load moment, this is my 37.427, this is 8.158, this is 35.54, this is 18, and this is 0. So now I'm drawing a line to ensure vertical consistency. Similarly, so using red as my line, so you see that FA plus 8.153 it boosts it, and 8.153. Then it remains, okay, one more of this, the point of this continuity. So it goes all the way constant up to here. Then this point load brings it down again. You can see, to be sure, 8.15, exactly 8.153, 53. Then comes again. Then this point load brings it upward again. Then takes it to this place again. Exactly. So here is minus 9.847. Here is 32. Okay. B is 27 points. Wait a minute. Okay, 27.58. So don't mistake it. 7.58. C prime is 32.42. Right, this is positive, negative, positive, negative. So that is for shear force, shear force, shear force. Continuing to extend this line. Extending it. Now, MA, which was obtained, was 40. Okay, MA was 35.54 because there's a moment there. 35.54. 35.54. Then moves all the way up because MD was 45.99. Then moves all the way down to 101.715. There is 35.54. There is 45 points. Don't mistake it, please. 99. Okay, I don't know how I'll do it because okay, let me do it again. Exactly. 45.99. So 101. Then it moves all the way. Okay, let's extend this line because remember when shear force is 0, that's the position where we'll be having maximum bending moment. So bringing it down. So maximum bending moment. So it goes up to 88.58, then it comes down to the moment value that was here, which was 174. 174.38. This is negative, this is negative, this is positive, this is positive. Well, this is 88. You can check the moment values. 0.38. Wait, this is 101.75. You can check. So 0 maximum. So that's it basically. Remember, and you will notice that where we had a straight line in shear force, we had a slant. Where we had a slant line in shear force, we had a parabolic curve. So let's call it a day. Thank you. And of course, the distance we got from here to here was 16.21. Thank you.